Okay, so this is going to be our last segment talking about kinetic theory. And so here's our fundamental idea. The average kinetic energy of molecules, so this is kinetic energy, is going to be proportional to their temperature. So as you raise the temperature, it's going to raise the average energy that the molecules have. Now what this means is there will be an average speed. So we're assuming that the m is going to be the same because it's the same molecules that are bouncing around in there. So that means there's going to be an average speed at which the molecules are going to be traveling at. But as they're moving around, so let's say that this particular molecule has a certain speed, and I'm illustrating how fast it's going by the length of the arrow. And let's say that it hits another molecule here which is going very slow. So I make a smaller arrow to represent that one. Now after the collision has occurred, maybe this one shoots off in this direction with a great deal of speed. And now let's say that this one, after the collision, then is going very slow. So these molecules are going to have a certain average speed. So when you take all of the molecules and you take all of their speeds and then you average them together, that's the average speed. But some of the molecules are going to be moving very slow, and some of the other molecules are going to be moving very fast. And they're constantly exchanging energy with each other and changing their speeds. So this graph right here shows a distribution of molecular speeds. And so what we have on this graph is going up and down is going to be the number of molecules that have that particular speed. And then going sideways on the graph is going to be the speed. So here you've got the slow ones over here. These are slow molecules that have very small speeds. And then over here is going to be the ones that have a lot of speed. And notice it makes a curve that does something like that. So for this particular temperature, there's going to be a certain number of the molecules that are going to have the average speed. But then notice that there are other molecules over here that are traveling slower. And then on this side over here, there's going to be a few of them that are going to be traveling faster. And notice that the average one is the one that has the most number of molecules. So there's very, very few molecules that are traveling very slow, and then there are very, very few molecules that are traveling very fast. Now what happens if we increase the temperature? So if we increase the temperature, we give them more kinetic energy, which means that the average speed is going to increase when we do that. And so what's going to happen then is we get the other curve there. So the other curve is going to be something that's going to look like that. And so now notice that the average speed is going to be higher. So here was the old average speed over here. Here's the new average speed, and it just got higher because we increased the temperature. Okay, and so you have a different distribution occurs when you increase the temperature. Okay, who cares? So this is very useful in explaining the process of evaporation. Now you all know that if you increase the temperature of water to 100 degrees Celsius, it starts to boil. And so it starts changing from a liquid into a gas. But did you know that water also evaporates at a lower temperature? So you could take a glass of water and put it on the counter and leave it there for a few weeks, and you would find that the water level starts to drop. Because even at room temperature, water can boil. Water is changing from a liquid to a gas. So how is that possible? So if you look at these distributions of speeds here, you will notice that even at a low temperature, there's always going to be a few molecules that are going to be traveling very, very fast. And so they're going to be traveling so fast, they're going to be able to break free of the surface of the water. And they leave the water, so therefore there's less water left over. So it has just evaporated. And given enough time, those water molecules will basically be able to jump up out of the water, and that water is going to evaporate. Now, if you increase the temperature, then that means there's going to be more molecules that are moving faster, so that makes it easier for the water to evaporate. And so here's another one. Why do you feel cooler when you sweat? So it's a hot day, you're perspiring, so you've got water on the surface of your skin that came from inside your body. So when the wind blows across that, it makes you feel cooler. So why does that do it? So you got water on your skin, and only the fastest molecules are going to be able to evaporate. So they're going to jump out of the water on your skin and are going to be carried away by the wind. The remaining molecules are going to have less energy because the energy of these fast ones has been carried away. So that means there's less energy in the water on top of your skin. And now that means that in order to heat that water back up so that more molecules can evaporate, where does that heat have to come from? You. So your internal heat is then going to heat up that water on the surface of your skin, and then it's going to evaporate. And so the sensation of heat leaving your body is cold. So your skin is going to feel colder when that happens. All right, let's take a break. And when we come back, let's see how work and heat and energy are all related to each other.